Cool. All right. First thing I want to show you guys is that I posted a sample lab report. So I just picked a data set. It wasn't ideal, it was a little too small, but it had 2 numerical variables and 1 categorical, which was the criteria. And so I think it was something on leukemia. It was a little bit of a somber data set. But so here I've posted both the HTML as well as the RMD code, okay, so that you can just follow along what I did and just know what's expected of you for this lab report that you're handing in at the end of the term. Okay. So without spending too much time on it, right, because you can go back and you can have a look, but I'm going through my data summary, and then so just talking about where I got this data from, what's going on, that's the first thing you did. And then we're just adding on to there, right? I summarized my categorical variable, then I made a bar graph, then I visualized both my numerical variables, etc. Right, so just going through all those questions. The one tweak that I did was I saved my scatter plot. I have a question for you, and you're allowed to do the same thing. So make a scatter plot of your 2 numerical variables. And then, so I just moved it to my regression analyses when I need it, okay, where I'm fitting the straight line. So I moved it to there. Doesn't matter. Okay. But like I said, so I posted that in its own folder, sample lab report. So you've got the RMD file, so you can see the code that I used, right? Feel free to work off of that one. You're welcome to use that, that's fine. And hopefully you find that helpful. Okay. We've got those lab times that I've stolen from Jason. Tuesday, Thursday, both this week and next week, but remember there's no labs on Friday this week and Friday next week because there's no classes at all. So how about that for our first note? So extra lab times. This week and next week. Oof. Tuesday, what did I say? Can't remember. I think between 12 and what? I feel like there's 3 hours on the that's the problem. 12 to 2 in C184. So that's our usual room, and then 2 to 3 in C286. And then Thursdays were 12 to 2 in C286 again. So that's just upstairs from where we usually are. I have to double check that they have R installed, but they should, so it shouldn't be a big deal. But also no labs on Friday this week. Yeah, that's so this week and next week. Tuesday, Thursday, Tuesday, Thursday. So there's an extra 10 hours of kind of lab office hours. Hopefully that's enough for you guys to crank out these labs. If none of those times work, then just let me know and we can meet at a different time. But hopefully we can make something in there work. So I'll just be in there and you just come whenever you want to. If you want to, with questions, we'll sort it out. Yeah. How long should it take you? It took me half an hour to make the report. I usually triple it for you guys. So if it takes me half an hour to make a solution set, for example, I usually times it by 3 for the amount of time that it takes you. So I don't know. I'm not expecting it to take long. It's just the little bumps in the road along the way, right? It has to knit properly and all that fun stuff. So, so I'm not actually expecting it to take that long, but I wanted to be available in case you guys had questions and problems. Okay. I had some notes. What did I? Oh, I have to do my evaluations. So have you guys done evaluations in your classes yet? Yeah. Anyways, we have to do mine. I'm thinking we'll do them on Wednesday. So now you know. Okay, so evaluations. At the start of class on Wednesday. There's really no good time to squeeze them in. I'm kind of annoyed we got them late. Otherwise, I would have done them earlier. I've been sitting on them for a while, but we had our tests and all that fun stuff. So, but now, got to get them done. So, here we are. Okay. Does anyone not have the examples that we're gonna go through? So I handed out a sheet of examples last day. It started with 5.3 and then on the back it has 6.1, 6.2. Save you guys some frenzied writing. Oh, and how could I forget? I'm bummed because they printed ugly, but I've got new and improved formula sheets. And I squeezed them into one page. So I'm pretty proud of myself. You'll notice they're the same, but because we're doing 6.2, I had that added on there. So. So this is the one you'll have on for the final. But like I said, I've cut some of those things, some of those sections that we weren't doing anyways. Yeah, I'm coming around. There you go. Come on. Come on. Set that timer. Logs me out too fast. Great. Okay. And don't worry, you'll get assignment 6 at the end of today. One thing I do want to say is that I will be dropping your lowest 2 assignment grades. And we have 2 more assignments left. So there's assignment 6 and assignment 7, which I'm squeezing in there. So if you're okay with your assignment grades as they are, consider those optional, right? But if you want to boost a chance to boost your assignment grades, then I would hand in assignment 6 and 7 and see where that gets you. Okay, so you know in advance I'll be dropping your lowest 2. And so I know this is a busy time, right? But it's also, you guys need to practice this stuff. So I want to give you guys the kind of the opportunity, and then you can kind of decide if you're okay with your grades as they are, or if you want a chance to boost them, then then you have that chance. Does that make sense? So like I said, consider 6 and 7 basically optional. As a chance to bump up your grade. So much paper. Thought I'd be fast enough. Okay. Fine. I think that's it for handouts. If you didn't get assignment 5 last day, then that's due on Wednesday, right? So make sure that I have to make photocopies, but there's a photocopier just down the hall. So just after class, let me know and I'll go grab you a photocopy. It should say up at the top. Okay. Cool. That's pretty good. I just feel like at least if you know in advance that you have this option, then it's like, well, if you didn't do it, that's on you. And you don't have to, oh, what's going on here? Worry about doing it if you don't have time. Okay. All right. Oof. I feel like there was something else I wanted to say here. Oh yeah, I will be dropping, kind of go on the record and say it. Your lowest 2 assignment grades. Yeah, so there's gonna be a assignment 7. So 7 assignments in total. Oops. So probably, yeah, I'll get you guys the assignment 7 on Wednesday. We probably won't have covered all the material until the Monday, but it'll be due on our last day on the Wednesday. So quick turnaround, but also it's quite a bit shorter than what we're used to. Okay. So, all right. Review. So last day we just started talking about proportions, right? So proportions are for categorical data. Proportions are for categorical data. And we said that p hat is a sample proportion. So just like before where we had X bar and mu, right? X bar is the sample mean, mu is the population mean. We have p hat now because we can't use p bar. P bar would be the average of p, right? So we have to use something else. So we have p hat as the sample proportion, and p, just plain p, is the population proportion. You can also use pi, right? If you want to stick to Greek letters, but I've tried to kind of go with how the textbook lays it out. Not that you guys have been reading the textbook, but just in case you did, then I wanted to match the textbook. And so that's why we have just P. But if you want to stick to Greek letters for populations, then pi is your man. Okay. So P hat, how we calculate P hat is we have some number of successes over a total sample size. So some number of successes over your sample size, which is still denoted by n. What's fun about proportions, I mean, if you think about it long enough, it's gonna kind of blow your mind, but even though it's categorical data, with enough of a sample size, then these values are actually gonna follow a normal distribution. And that's how we can calculate probabilities again, right? And so proportions follow a normal distribution, but because this is kind of weird, we're gonna have to check some assumptions, right? So there are some assumptions that have to be met. And so for proportions questions, if you're looking at assignment 6, then I ask you to check the assumptions that for inference are satisfied. So proportions follow a normal distribution. Assuming the following are met. First one, that we have a random sample. That seems reasonable enough. Right, we have to have a random sample to make sure that it's representative of the population. Fair enough. Here's kind of a weird one. We have to have a large enough sample size, but not too large. So it can't be larger than 10% of the population. And that's just kind of something to remember. It doesn't really make sense. We're kind of taught that, okay, larger samples the better, larger samples the better. But once we've taken up too much of the population, the idea is that even if you have a random sample, the individuals in there aren't going to be independent, right? So if you've taken up too much of the population, you're going to have siblings in there and people from the same town and whatever, right? So so then you lose that independence between people in your sample. So that's the reasoning. But as long as you remember that n has to be less than 10% of the population, that's good enough for me. So these 2 points, you would just argue either they're given to you in the question or we're assuming these things, right? So then you would just say it's reasonable to assume that a sample size of 600 Americans is less than 10% of the population of Americans, for example, right? So the third thing that we check, here's where we stray. We said, okay, well, there's going to be a difference between if we're doing a confidence interval or a hypothesis test. So we'll start with the confidence interval assumptions. So for a confidence interval, so what you're going to do is you're going to read these questions and figure out, okay, am I going to do a confidence interval? Am I going to do a hypothesis test? And then you only have to check the assumptions that apply. On the assignment, I'm making you do both. On the final exam, you only have to do one, right? So it'll either be a confidence interval or a hypothesis test, right? So you only have to check the assumptions that apply. So for a confidence interval, we have to check that n times p hat is greater than 10. N times p hat is the number of successes, right? So looking back at p hat over, so p hat is the number of successes over n. If I multiply n over, then I have n times p hat is the number of successes. So really, I just need to make sure that I have at least 10 successes and 10 failures is the second condition. So at least 10 successes. And the fourth one is that NQ hat is greater than 10, at least 10 failures. So I have to have at least 10 successes and 10 failures in my sample, making my minimum sample size 20. If I've collected a sample size of 20 and I only have 5 successes, I have to keep collecting until I have at least 10 successes and 10 failures. Right? And that's just to be able to detect if there's a difference. Yeah. Oh. That goes in here. Everyone's got the same question. So where Q hat is 1 minus P hat. So it's the proportion of failures. All right, so P hat is your proportion of successes and Q hat is your proportion of failures. And on your formula sheet, right, I've got in the bottom corner there where Q is 1 minus P. So in general, wherever you see a Q, it's just 1 minus P of that. Right, so we're going to be talking about Q naught. So Q sub 0, we're going to be talking about straight Q and Q hat. All of those are just 1 minus the P equivalent. Okay. For hypothesis testing, so formal hypothesis testing, the third condition that we check is that n times P naught is greater than 10. So at least 10 hypothesized, or I'm going to say expected successes. And the fourth one is that NP naught is greater than 10. Oh, sorry, that's the same thing. NQ naught. At least 10 expected failures. Oops. Been typing all weekend and writing's a little tough now. So where P naught comes from your null hypothesis, where P naught is from the null hypothesis that P is equal to some hypothesized proportion. So P naught is from your null hypothesis, so which means you have to do a hypothesis test to be able to check that condition. So a lot of the time I get questions saying, oh, I've got this confidence interval, but I don't know what P naught is, right? And you shouldn't be checking it. If you only have to do a confidence interval, you don't have to check it. So P naught is whatever you want to compare your sample proportion to. Just like in the mu naught case, right, for one sample mean, we had some sample mean that we wanted to compare to some number, right? And that number was mu naught. So now we have some sample proportion that we want to compare to some hypothesized proportion P naught. Okay. Before we do an example, what's fun about proportions is that we can figure out what sample size we need in order to satisfy certain criteria. Okay? So this is new. So for sample size calculations, as long as we have some desired margin of error and some desired confidence level, so with some desired margin of error, which I think we've talked about maybe once, okay, but I'll show you what it is. And desired confidence level, we can calculate the sample size needed. So the idea here is, okay, well, if you want to estimate some proportion, and let's say you need funding for this project, right? They're going to ask you, okay, well, what sample size do you need and how much is it going to cost you? So then you have to say, okay, well, what sample size do I need, right? And so you're going to say, okay, well, I want to be able to estimate this proportion to a 95% confidence interval, let's say, right? So that's your confidence level. And your margin of error is your plus minus chunk of your confidence interval, right? So what do you want that plus minus chunk to be? Okay. So for a confidence interval, for proportions, we have p hat plus minus z star times the square root of p hat q hat over n. Z star behaves the same way, and we've already found it. We haven't necessarily called it Z star yet, right? But so if you want a 95% confidence interval, your Z star 1.96. Right? And so if you want a 90% confidence interval, your Z star is 1.645. So this plus minus portion is called your margin of error. The tricky part is that, okay, well, p hat, that's from the sample. We haven't collected a sample yet. We don't even know what sample size we need, right? And so for sample size calculations, use n. I'm just going to give you the formula. Usually I would derive it with you guys, but you only need to know the formula, because I think that's what you would use. N, your sample size, is going to be your Z star over M, which is your margin of error. I'll make a note of that in a bit. All squared times P star Q star. Where Z star, so I'm just going to outline everything that's on here. Where Z star is the Z value for the desired confidence level. M is the desired margin of error. Oops. P star for these calculations, and there's lots of ways that we can do it, but I'm going to go with the most conservative estimate, P star is going to be 0.5, always. And so Q star is 1 minus P star, which is 1 minus 0.5, which is 0.5. Right? Yeah, for sample size calculations, you're going to use a 50-50 split is essentially what's going on. Right? So you're assuming that your population has a 50-50 split, but that's also going to give you the highest possible sample size that you might need, right? So if it turns out that you have a 30-70 split, then you have too big of a sample, but don't worry, it's not a problem. Okay? So this is going to maximize your sample size that you could possibly need. Okay? So let's see here. I think I have on those examples. I'll do a quick one here. So here's a little example. Say we want to estimate a proportion with 99% confidence and a margin of error no greater than 0.03. What sample size will we need? So we could start and say, okay, well, I know my margin of error is this plus minus chunk, and then we could morph it into a calculation for n, or we'll just jump right into and use the n formula. But I want you to kind of see that you don't actually need this n formula, but I give it to you anyways. N is Z star over M squared times P star Q star. Z star, ideally I would write down where I got Z star from, right? So using the table C with a confidence level of 99%, I find that Z star is 2.576 over my desired margin of error, 0.03, right? So I'm saying I want to have this proportion to within 3%, right, or 0.03. Squared times, and then here's where we just always use the 50-50 split. .576 divided by 0.03 squared times 0.5 times 0.5. I need a sample size of 1,843.2711 repeating. We can't actually sample 0.2711 of a person, or of a manatee, or of anything for that matter, right? And so we have to round up. So even though technically we should be rounding down to the whole number, right? But because we need to have at least this sample size, we have to round up to the whole number. Okay? So we would need to sample 1,844 individuals since we can't sample 0.2711 repeating of a person. Right. Remember, these are categories. So how would you quantify the hair color of 0.2711 of a person? You can't. Right? You'd have to sample another person. Okay. So that's how you're going to calculate sample sizes. The only sneaky part is the P star Q star, right? But as long as you remember that, okay, P star Q star, those are just 0.5, 0.5. Just assuming that you have a 50-50 split before you even start sampling. Cool. Any questions about that one? So there's another example in the examples that we're about to do. All right. We ready for this example? So example for one sample proportion. This one's kind of wordy, but I don't know. I stole it from a textbook. So two scientists want to know if a certain drug is effective against high blood pressure. Seems reasonable. The first scientist wants to give the drug to 1,000 people with high blood pressure and see how many of them experience lower blood pressure levels. And then the second scientist wants to give the drug to 500 people with high blood pressure and not give the drug to another 500 people with high blood pressure and see how many in both groups experience lower blood pressure levels, which is probably what we should be doing. The first option, although it seems kinder to give this medication to everyone, we wouldn't actually be able to see if there's a difference, right? Maybe all their blood pressures just dropped because now they're relaxed because they took the drug or whatever, right? And so we should be picking the second option where 500 get the drug and 500 don't. I'm just stealing this example here. So, gonna need, we've got, can't multitask, I guess. There. But if you don't have a copy, let me know, I'll get you one. Okay. And so the GSS, and for, I don't know how many terms, I had no idea what the GSS was until finally I Googled it. It's a general social survey. Seems reasonable. So the GSS asks the same question. Below is the distribution of responses from the 2010 survey. So they surveyed a total of 670 people, right? And they asked them, if you were to do this, which one do you think would be, which option do you think is more appropriate, right? And seeing how many people would select that second option. Because we, in our minds, we kind of know that we have to have something to compare it to, right? The changes. And so 571 people said that, okay, go for option 2. That way you can see if there's any changes. 99 people said that all 1,000 get the drug. Right? And so depending on which of these groups we're talking about, right, that's going to determine which is our success, right? And so first thing we're going to do, I guess, is check that the assumptions for inference are satisfied before we even do anything. But like I said, the assumptions are going to depend on whether we're doing a confidence interval or a hypothesis test. Of course, in this example, we're going to do both, right? But so you're going to read through all the sections and see, okay, am I going to do a confidence interval or a hypothesis test? Okay. And so part B says that the GSS found that 571 out of 670 of Americans answered the question on experimental design correctly. Do these data provide convincing evidence that more than 80% of Americans have a good intuition about experimental design? Kind of a weird worded question, but we get the idea, right? So we've got this sample proportion of 571 out of 670, right? That's our sample proportion. We want to see how does it compare to 80 specifically. Is it going to be more than 80%, right? Or 0.8. Part C, use a 95% confidence interval to test the hypothesis. Does it appear that more than 80% of Americans have a good intuition about experimental design? Okay. And so we're going to do a hypothesis test and a confidence interval. So I'll just make a little note here. So hypothesis test and confidence interval. So we have to check all our conditions. The first one is, do we have a random sample? It doesn't say explicitly, right? But it's an official survey, so hopefully they're random. So safe to assume sample was randomly selected. So you're just going to argue whether you have a random sample. Sometimes it'll be in the question, right? You took a random sample of 670 people, for example. Or you just have to argue it in some way. Our second assumption is that our sample size has to be less than 10% of the population. So our sample size, right, is 670, has to be less than 10% of population, I think just of Americans. Yeah. So you can just say something like that. And I think I told you guys last day, but even if you just list the generic assumptions, that's worth a good chunk of marks in my books, right? It's a lot to memorize at the end of term. I know they don't come naturally, right? So if you want to do just the bare minimum, I guess, then I'd say out of 2 marks, then giving me just the generic assumptions, I'm a mark and a half out of 2. That's still pretty good, right? So you can take it that extra step further, but if it's just not clicking, then just memorize these assumptions and move on. So third thing we're going to check is, let's check for the confidence intervals first. The n times p hat has to be greater than 10. N is 670, right? Or really, we know the number of successes, right? We're talking about successes. How many people answered 500 get the drug and 500 don't, right? So 571 successes is more than 10 successes. 571 is greater than 10. I just put a little check mark saying, yeah, it is. And Q hat has to be greater than 10. We know that the number of successes is, or failures, sorry, is 99, which is greater than 10. For hypothesis testing, Just keep numbering, I guess. We have to test that NP naught. NP naught is N, which is 670, times P naught, which is 0.80. Reason for that is that we want to test the null hypothesis that P is 0.80. Right. Yeah, so NP hat is the number of successes and NQ hat is the number of failures. I'm also looking at the descriptions. Yeah, so you do have to have an idea of what your successes and what your failures are.
Like, how would you determine what is a failure?
Oh, so here, in part B, for example, right? So do the data provide convincing evidence that more than 80% of Americans have a good intuition about experimental design? So that would be the 571, right? So then if they answered B, that's a success. I'll make a note of that on here, actually. Oh, I don't have it yet, but I will. Because I know that's tricky. Okay, and another tricky thing, right, is knowing P naught before you've set up your null and alternative hypothesis, right? But that's why you have to read ahead and figure out, okay, well, if I'm doing a hypothesis test, what's my P naught? And in this case, it's going to be 0.8. So 670 times 0.8 is 536, which is greater than 10. Great. What are we checking here? We're checking that, okay, if the proportion is 80, we would have expected to see 536 people say yes. We saw more than that, right? So we suspect that it's more, right? We just want to know, is it significantly more? So then our last assumption is that NQ naught, N is still 670, times Q naught, which is 1 minus 0.8, 0.2, which is 670 times 0.2. Or if you wanted to, just 670 minus 536, but I like to stick to the calculations. These are always going to check out, right? You're never going to have a situation where the assumptions aren't satisfied. It's just a matter of you have to jump through these hoops to check it. Just out of the blue. It's just a fact. So we have to have at least 10. And the idea is that we have to be able to detect these changes. Right? If everything's too small, then we can't see any changes. No, you'll have to memorize it. Yeah. It's just 10. Oh. So, but like I said, because I know these assumptions take a lot out of you, if you just crank out exactly like that, that's, I'd say, a mark and a half out of 2. Okay, so without doing anything with the question, you can still get those assumptions if you just memorize all of that. But I think once you do a lot of practice problems, then it won't be so bad. So now we can actually go ahead and answer the question. So part B, oops. the GSS found that 571 out of 670 of Americans answer the question on experimental design correctly. Do these data provide evidence that more than 80% of Americans have good intuition about experimental design? First thing we're going to do is I'm going to calculate my p hat, my sample proportion. P hat is my number of successes over n. Which is 571 over 670. Point 8522388806. Ideally, you would just keep this whole number in your calculator, right? So you're going to use that store function and just use it. If you must round, then keep around 4 decimal places. Okay. So if rounding, keep at least 4 decimal places. But I'm going to store it in my calculator. And like I said, if you need help figuring out how to store stuff on your calculator, I'm happy to help because it is a handy function. So you're going to keep at least 4 decimal places if you absolutely must round. So now we've got our sample proportion. Our sample proportion is essentially 85%, right? 85.2%. And so that is higher than 80%. We want to know if it's significantly higher than 80%. And so setting up our null and alternative hypotheses, notice that I haven't even gone through the formulas with you guys, because at this point, if we're doing a hypothesis test, then you know that, okay, well, I'm going to pull my null and alternative from the formula sheet, and then the calculation that follows, that's how I'm going to do my test, right? And then depending on now we're going to be back to Z's, right? Nice familiar territory, right? So we don't have to deal with any degrees of freedom or anything like that, but we know how to deal with Z scores, right? So now it's just a matter of, okay, do I have a T or do I have a Z? And then from there, you can find your p-value the same way that we've been doing, right? So we're really not doing anything new. It's just a different type of problem. So step 1 is to state our hypotheses. Our null hypothesis is that P equals 0.80, because we want to know, do these data provide convincing evidence that more than 80%, right, answered the second option? So our alternative hypothesis is that P is greater than 0.80, making this a one-sided test. Right, because you're only concerned about one extreme. Step 2. Do the test. Do the test means do whatever calculation follows on your formula sheet. So for proportions, for one sample proportions, we've got Z is P hat minus P naught over the square root of P naught Q naught over N. just make a little note here, right? That 0.80 is your P naught. So what's fun about proportions is how little information you need to do this calculation, right? You only need P hat, which you need your number of successes over your sample size, but that's it, right? And then you need your hypothesized proportion, right? What are you comparing this proportion to? And then your hypothesized proportion pops up again. Then 1 minus that is your Q naught. Q naught is 1 minus P naught. And then your N, which is your sample size again. So really, you only need to have your number of successes and your sample size and your hypothesized proportion, which to me feels like a lot less information to have to handle than for a means question. So proportions are kind of fun that way. So we've got our proportion, our sample proportion of 0.8522, sure, 38806. But like I said, if you have to round, then go to 4 decimal places. Minus our hypothesized proportion, 0.80. Over the square root of 0.80 times 1 minus 0.80. All over N, your sample size is 670. Yes? Yeah, if you don't want to show the 1 minus 0.8, I just want to show you where it's coming from, but if you go straight to 0.2, that's fine. Yeah. Cool. So it's the same idea though, right? We're just seeing, okay, well, Z tells us how many standard deviations, right, or standard errors we are away from this hypothesized proportion, right? So we're just seeing how far is this from this? Same thing that we have been doing all along. Okay. So minus 0.8. I'm going to write out all my steps, or most of them, but that's just so you can check that you're calculating things correctly. Okay. So 0.0522388806 over the square root of 0.8 times 0.2, 0.16 over 670. 0.0522388806 divided by, and don't forget that square root, 0.0000. 1, 2, 3. 238806. Weird. Square rooted. 0.0522388806 divided by 0.015453348. Finally, 3 divided by that can't be right. Did you guys get a huge number? Oh, never mind. I got like 213. It should be 3.38.
Just want to confirm for the previous calculation of when you scroll up and you had the 0.8 minus the bracket 1 minus 0.8.
Yeah. Should be 0.8 times 0.2.
Oh, it's times, okay.
Yeah. Good. So I get 3.3804199916. Z, we can round to 3 decimal places, right? We have to have the same number of decimal places that the table gives us. So now that we have our Z, we're ready for step 3, find the p-value. Same blurb we've been using, so using table C, I was about to say with degrees of freedom equal to whatever, but we don't have any degrees of freedom, right? Because we've got a Z. So we find that the absolute value of Z equal to 3.380, I'll go to 4, is going to be between 3.38, we're maxing out the table, 3.291. And technically, if you want infinity, all that you know is that it's greater than 3.291. If you want to leave it blank and don't put the infinity, then don't. Okay. So we need a one-sided p-value. Okay. So our one-sided p-value I use the same setup for all of these, right? I still use the less than signs. And that way I'm not mixing up my inequalities, my less than greater thans, right? If I'm always using the same setup and just keeping track of, okay, when I read these p-values, I have to switch the sides, then it's easier to keep track of. So my one-sided p-value must be less than 0.0005. If it's less than that, but it has to be greater than 0. So technically, but I'll just say that this is optional. And this is optional. So that's an important distinction, right? Is because our Z is, we know it's greater than 3.291. So the upper cap is, all we know is that it's greater than infinity, or less than infinity, sorry. And then whereas our one-sided p-value, all we know is that it's less than 0.0005. So the lower cap must be 0. Right? We can't have a negative probability. Okay. Cool. But all we really needed out of this was that the one-sided p-value is less than itty bitty, 0.0005. So for our conclusion, step 4, same conclusion that we've been using, right? We use our p-value to either reject or not reject our null hypothesis. So since our one-sided p-value is less than, right, all we know is that it's less than 0.0005, it is, well, we know for sure if it's less than 0.0005, it's definitely less than our alpha level of 0.05. So it is less than our alpha level of 0.05, which means we have enough evidence to reject H0. If we're rejecting it, we can say in favor of what, right? In favor of HA. Therefore, we can say more than 80% of Americans. And we just reword the question as an answer. It was a kind of a weirdly worded question to begin with. We can say more than 80% of Americans have a good intuition. I don't know about that. Good intuition about experimental design. What if we use the confidence interval instead to test this hypothesis? So use a 95% confidence interval to test this hypothesis. So like I said, on the final, I'm not going to make you do both, just one of them, right? But obviously our in-class examples, we cover both, but also on your assignment, I make you do both, just so you get comfortable doing both. And then on the final, it'll be one of the two. So use a 95% confidence interval to test the hypothesis. Because we haven't seen the confidence interval formula yet, well, briefly for the margin of error, I'll just write it down so we can have a look at it. We use p hat, that's our sample proportion, times z star, which we already know how to find, times the square root of p hat q hat over n. Notice the difference. So in the means questions that we have been doing, right, what's in our, it's easier on your formula sheet, right, what's in the square root on our t or our z has been the same as the confidence interval, right? That's not true anymore for confidence intervals. Okay? And so notice that we have a different square root, right? Earlier in our square root, we had p naught q naught. Okay? Now in our square root, we have p hat q hat. Making confidence intervals nice that way, because then we don't even need to have a hypothesized proportion. We have one because there's a hypothesis that you want to test, right? The same one. But we only need p hat and q hat and n for a confidence interval. So we want to test the null hypothesis that p is equal to 0.8 again, and the alternative hypothesis that p is greater than 0.8. So for a 95% confidence interval, right, we have to find our z star. So using table C, with a confidence level of 95%, we find that z star 1.960. Because we want a z star. So if you have a t star, then you need your degrees of freedom. But for z, z is just nice and just tiny at the bottom. Yeah. Yeah, so it's going to depend on if you've calculated a z or a t, or if you need a z or a t. Nice. Okay, So now we have our Z star. And back in my day, we had to memorize the Z stars. So you're welcome. Feels like overkill, but we had it rough, okay? I think my prof just didn't want to print out tables. Anyways, let's do our confidence interval. So p hat is plus minus Z star times the square root of p hat q hat over n. P hat, remember we've stored it hopefully. Oh, I think I just overwrote it. What was it? 571 over 670. There. Oops. So we've got 0.852238806 plus minus Z star, which is 1.960 times P hat 0.852238806 times 1 minus 0.852238806 over n, which is 670. Q hat. It's gonna, yeah. Yeah, so the P's and the Q's go together. And it doesn't matter what kind of P you have, you can find the Q. That makes sense. So, all right. 1 minus that times that. I'm gonna do most of it in one go. Divided by 670. So I get plus minus 1.96, only because there's so many decimals. I don't want to write them out a ton of times. 0.00. Oh, did I do my square root? I wonder. One minus recall 1 divided by 670. Square root that, I did. Point 0.014850559. Is that what you guys are getting for that? Once you take your square root. Times 1.96. 0.0291070095. That's my margin of error, right? 2.9%. (0.8522388806). Recall 1 minus recall 2. So I would store that margin of error so that I can find 0.823131711 up to recall 1 plus recall 2. 0.88134591. Getting the same thing.
Sorry, you said something. What's the 0.029?
So this is your margin of error. Right, so as a decimal, 0.029, Or if you wanted to talk about it as a percentage, that would be 2.9%. Right? Yeah.
For that calculation of the all square root, I'm getting a little
Ooh, little less, huh?
0.01%.
It, have you stored it or have you or you're entering? And you're storing the 571 over 670? Because it could be that it's carrying more decimal places.
Yeah, just the 1 minus the 8522, multiply that by 522.
With all the decimal places? Oh. Let me try it again. Well, first I'll do 571 over 670. Store that in 1. Then I'll do 1 minus recall 1 times recall 1. Square, nope, not yet. Jump the gun. 1 minus recall 1 times recall 1 divided by 670. Square root that. You're right. Sorry, guys. Good thing I wrote it out so you guys can check it. 0.013709558 times 1.96. .0268707. Is that jiving? Great. I'll store that. And then these will change. .825368073. .879109539. Okay. Now we have to use our blurb quickly. I know I'm running out of time. So we are 95% confident the interval from 82.5% to 87.9% captures whatever we were asked to make an interval of. Captures the proportion of Americans. Now we're talking of all Americans. Proportion of all Americans with good intuition about experimental design. Since this interval is consistently over 80%, right, we have enough evidence to reject the null hypothesis. Since this interval is consistently over the null hypothesized, P is 0.80. We have enough evidence to reject H naught. Then say what that is for the question. Try part D, because we've already gone through it. It's finding the sample size. And then don't worry about the assumptions, but take a stab at the 2 sample proportions. I'm confident that you can do it without us going through it quite yet. We'll go through it, obviously, but try it. So if you need assignment 5, I'll go photocopy you some.
I have a question for the homework 5.
You got it.